Plenty points available. Go get them. And once again yesterday, my wife insisted on going through her ritual in which she engages about every 3 months of insisting on dyeing my hair. It isn't the case that a can of brown paint fell on my head. Vanity is a questionable character at best. We'll let it go at that. All I can say is, if it keeps her happy, it helps keep me happy. Enough said. Now then, as we mentioned last time, we know calcium carbonate saturated in straight deionized water gives a pH on the order of 10. Therefore, on considering the solubility in a water solution buffered at pH 8, where the only impact of the buffer is to maintain system pH, we know before we do any calculation, the solubility of calcium carbonate in this pH 8 system has got to be greater than it is in deionized water, where you get to pH 10. Because this is pH 8. This is 100 times more acidic than pH 10. And the more acidic the system, the more effectively you murder bases present. And the base in question in this case is carbonate ion. So specifically, the more effectively carbonate ion is murdered, the more soluble calcium carbonate becomes. That we know before we do any arithmetic. And we also said, to do this analysis, let's use this equilibrium. Reasonable. Well, we recognize that when we wrote this equilibrium, the standard KSP equilibrium for calcium carbonate, and applied it to the pH 10 deionized water system, you can't calculate S from this. You got to factor in Kb carbonate. And after factoring in Kb carbonate, we found out that carbonate hydrolyzes about 70%, 69% to be on the nose. So this equilibrium, although it applies to the system, is certainly not a stoichiometric statement. This does not account for the considerably basic nature of the system, pH 10, nor does it account for the conversion of carbonate to bicarb, as well as hydroxide ion. So you got to be careful with this stuff. So when we go to pH 8, after already realizing that the calcium carbonate is going to be more soluble, if carbonate disappeared to an extent of 70% at pH 10, to what extent is carbonate going to disappear at pH 8 relative to 70%? Greater or smaller than 70%? Greater, of course. We're letting this stuff talk to us. And on what basis is it talking to us? Acid-base stuff that we did in chapter 18. So, last time we wrote the K for this equilibrium, evaluated K, which we found to be the product of KSP calcium carbonate and Kb carbonate. As it follows from this statement, calcium carbonate on the left, so we know in evaluating this K, we got to have KSP calcium carbonate in the numerator. And implicitly we see carbonate on the left, and these two hydrolysis products of carbonate. So we also know this thing's got to contain Kb carbonate. There it is. Put in the numbers for KSP calcium carbonate and Kb carbonate. Get 1.3 times 10 to the minus 12. And we also reminded ourselves that this too is a legitimate KSP expression for calcium carbonate. Why? Because it shows the chemistry that, or reflects the chemistry that takes place when calcium carbonate is dissolved in water. In fact, it does a better job of reflecting the chemistry that calcium carbonate exhibits when it's dissolved in water than this. But that's the standard textbook way of expressing KSPs. And in the KSP written in this fashion is always applicable, as long as the system contains a measurable molarity of the component ions of the salt. I mean, I say that because we've already reminded ourselves. If you want to get KSP for silver oxide or silver sulfide or copper sulfide or any semi-soluble sulfide, you can't have the metal ion molarity multiplied times the sulfide ion molarity because there's no sulfide ion in the system. You can't have the KSP depending on oxide ion molarity. You won't find any oxide ion in the system. At least not dissolved oxide ion. And we also know that S, the solubility of calcium carbonate, is equal to the equilibrium molarity of calcium ion, because when calcium ion goes in solution, it doesn't engage in any further chemistry. But carbonate ion does. So we wish to answer the question, how does the solubility of calcium carbonate relate to carbonate ion? Well, the way it relates is, it's the sum of the molarities of all possible forms of carbonate-containing things. So you got carbonate ion itself, or if carbonate ion collects one H+, it becomes bicarb ion, and if that collects an H+, carbonate ion collects two H+, you get quote-unquote H2CO3. So S is also equal to the combination of these molarities. So when we look at this equilibrium constant expression, we know this is S. The system is buffered at pH 8.00, so this is fixed at 1.0 times 10 to the minus 6. So if we're going to calculate S, we have to find out how the equilibrium molarity of bicarbonate ion relates to S. Otherwise, we got one equation and two unknowns, and we're stuck. So I wrote that over here. To solve this, we got to answer this question. How does bicarb relate to S? And we talked about this last time. What we need to do is to consider equilibria, which interrelate the molarities of the various forms of carbonate-containing things to each other. So, to interrelate, quote-unquote, H2CO3 to bicarb, we could use Ka, H2CO3. Or we can use Kb bicarb, which I used. To interrelate the equilibrium molarities of bicarb and carbonate ion, we can use Kb carbonate. Or Ka bicarbonate, which I used. Either works, doesn't make any difference. So I'm using Ka bicarb to interrelate the molarities of carbonate and bicarb. Here's the equilibrium constant expression. This is fixed at 1.0 times 10 to the minus 8. System's buffered. And if I rearrange this ever so slightly, I get bicarb molarity divided by carbonate molarity equals the hydronium ion molarity divided by Ka. If I put in the numbers, I get 210 to 1. To get a handle on the equilibrium concentration ratio between quote-unquote H2CO3 and bicarb, I go back to Kb bicarb. I rearrange this so bicarb comes on top, H2CO3 comes on the bottom, and that tells me the bicarb molarity compared to the H2CO3 molarity is equal to the hydroxide ion molarity divided by Kb. And you might well ask the question, well, why didn't I have this as H2CO3 over bicarb? Why didn't I have this as carbonate over bicarb? Because I've already sniffed through this system, and I know the bicarb molarity will be by far greater than either the carbonate or H2CO3 molarities. If I did this arithmetic, and I got a ratio that was smaller than 1, like 1 to 25 or something like that, I'd invert it. Because I prefer to deal with numbers that are bigger than 1 than numbers that are smaller than 1. But there's nothing, you can do it any which way you want. I just like to make the arithmetic as convenient for myself as possible, to eliminate arithmetic goofs. So, after establishing these ratios, bicarb molarity in this pot is 210 times greater than carbonate molarity. Bicarb molarity in this pot, the pH 8 buffered pot, is 42 times greater than the quote-unquote H2CO3 molarity. What do I now know? I now know that for carbonate-containing things at pH 8, only one of these is of consequence. And that's it. That's what this arithmetic has told me. And students will ask, well, how do I know where's the cutoff point? Like if the ratio is 2 to 1, can I do that? What does your arithmetic horse sense tell you? If bicarb to carbonate was 2 to 1, could I throw away carbonate? Heck no. It was 5 to 1. Could I throw away carbonate? No. But at 210 to 1, I'm going to throw away carbonate. Now, if you don't want to throw away carbonate and keep the carbonate in there, you'll find out it will not change the result of the solubility calculation at all. And this is the part of the puzzle that you won't really get a handle on unless you sit down with paper and pencil and do this yourself. Because this is the part of the puzzle where, in order to appreciate it best, by doing the arithmetic will talk to you. And you'll develop a feel for this stuff. There's no other way to do it. You have to do it. So I wrote, based on the consequence of what we have recognized, that the equilibrium constant value of 1.3 times 10 to the minus 12 is S for calcium ion molarity, S times bicarb molarity, times hydroxide ion molarity. Solve it for S, I get 1.1 times 10 to the minus 3. And here is once again the calcium carbonate solubility at pH 10. Hey, this is about 8 times bigger than that. Remember? Before we even tackle this arithmetic, we knew the solubility of calcium carbonate had to be greater because this system is more acidic. And we found that it's greater. Point, if I went through some arithmetic here and I calculated a solubility value which was on the order of this or smaller than this, I would stop. And I did something wrong, I don't know what it is, but let me backtrack and find out what it is. And that's the horse sense which you need to develop when you do science. You can't believe flatly in calculation. Because if the calculation you did is wrong, it doesn't make any difference whether or not you did the calculation correctly, because what is wrong is you did the chemistry incorrectly. Okay, enough on that for the moment. Well, let's make one more comment. Our next attack on the solubility of calcium carbonate in a water solution that has a fixed pH, a buffered system, will be calcium carbonate in water solution buffered at pH 6. We'll be doing that shortly. So when we tackle a pH 6 buffered system, how will the solubility compare to 1.1 times 10 to the minus 3? Greater. With what we have on the board, could we immediately pursue the pH 6 issue? I'm asking that you let this and this talk to you. Okay? So let me show you how to let this talk to you. pH 6. This is at pH 8. What is this ratio going to become at pH 6? What will it be at pH 6? It's 210 to 1 at pH 8. What's it going to be? What's this bicarb to carbonate ratio? What's this going to be at pH 6? pH 6 compares how to pH 8 from a hydronium ion concentration ratio? pH 6 is how much greater? 100 times greater. Well, doggone it, there's the hydronium ion concentration, 1.0 times 10 to the minus 8, isn't it? So let's change that to 1.0 times 10 to the minus 6, which means we're going to take that 210 to 1 ratio and multiply it by 100. Right? Because hydronium ions at the top of Ka. So if I multiply hydronium ion by 100, the ratio becomes 21,000 to 1. Well, we threw away carbonate at 210 to 1. What are we going to do with carbonate at a ratio of 21,000 to 1 in favor of bicarb? Bye-bye carbonate. Way bye-bye. But how about H2CO3? Because the more acidic the system becomes, the more effectively carbonate is protonated, isn't it? Which means the H2CO3 molarity is going up, while the bicarb molarity goes down. So let's look at hydroxide ion over Kb. Because when we take this thing to pH 6, the hydroxide ion molarity changes from 1.0 times 10 to the minus 6 to what? 1.0 times 10 to the minus 8. Ha ha! This ratio becomes 0.42 to 1. Which is now the principal carbonate containing thing in the system at pH 6. It's the H2CO3 stuff. But at 0.42 to 1, is HCO3 minus still a species whose concentration has to be considered? Yeah. You're damn right. So keep that in mind when we hit the pH 6 system. Recognizing you already know how to do it. All right. Now, in proceeding through the topics considered in Chapter 19, from a chronological order standpoint, we'll go to subtopic C and talk in brief about the salt effect. The salt effect relates to an area of particular interest to myself and to many other people who spend a lot of time thinking about chemistry and water solution. The special or specific area of interest to which I refer is called activity. I mentioned activity before. Did you hear about activity in 2045? I think I asked this before. I see no hands. Did you hear about the Van Hoff I factor in 2045? Then you heard about activity. If the people teaching 2045 and talking about the Van Hoff I factor didn't talk to you about its relationship to activity, they're not doing what the hell they're supposed to do. Activity, simply put, measures the ability of particles in solution to behave individually. Activity also relates to gases. Are gases or molecules in the gas phase behaving totally independent of each other? Or because they're present at high concentration, which means they're close together, pressure's high, and a low temperature, which means their average kinetic energies are not great. Now when they bump into each other, they tend to stick, and interparticle attraction forces begin to dictate the behavior of the system, which lowers activity. Except that physical chemists invented a different term for activity of gases. They call it fugacity. Funny sounding word. F-U-G-A-C-I-T-Y, fugacity. Well, we're not going to talk about fugacities, but should you ever come across fugacities, you're talking about activities of gases. And we're really not going to do anything for which you would be held responsible regarding activities. Activities in the main, as yet, although a lot of chemists are very interested in this, activities in the main remain, activities for the most part remain a can of worms. By that I mean there's not much understood about activities. I mean, if you take a swimming pool, for example, full of water. You see, if I got this room full of air, which I do, and here's an oxygen or nitrogen molecule over here, or a CO2 molecule, or a water vapor molecule, but most often I'm going to encounter a nitrogen molecule about 79% of the time, or an oxygen molecule about 21% of the time. Okay. If I go like this, I just bump some of these molecules. But there's a lot of space between these molecules in the gas phase. So when I go like this and bump these molecules in the immediate vicinity of my index finger, I'm not affecting the molecules over there and up here and down there. But in liquid phase, that's not true. If you take a swimming pool full of water, and somebody does a dive off the diving board, every molecule in that system has had its behavior affected. Why? Because the molecules in the liquid phase are all in contact with each other, aren't they? Therein lies the difference. So activity involves trying to figure out how the guy who does the belly smasher off the diving board at that end of the pool affects the molecules at this end of the pool. And that is a very difficult problem. Just devising experiments is very challenging and very demanding to get at this problem. But that is what salt effect relates to, in simplest possible fashion, for our purposes. We've already recognized that a material like silver chloride can have its solubility calculated directly from its KSP, because neither silver ion nor chloride ion have any Bronsted-Lowry acid-base properties of consequence. Chloride ion, obviously because it's the conjugate base of a strong acid, HCl. And silver ion, because even though silver ion forms a defined hydrate, its Ka value is damn small. So KSP gives us, at normal laboratory conditions, a solubility of 1.3 times 10 to minus 5, given that this is the square root of KSP for silver chloride, which is 1.7 times 10 to minus 10. So now, let's imagine I'm in the laboratory. I know about this property of silver chloride. If I take the ionized water and saturate it with the silver chloride and make measurements of molarity for silver ion and chloride ion respectively, that's what I'm going to get. Well, one day in the laboratory, while being interested in the solubility of silver chloride once again, instead of grabbing the ionized water, I inadvertently grabbed 10th molar sodium nitrate solution. I saturated a 10th molar sodium nitrate solution with silver chloride. I said, well, you know, and sodium ion. I mean, here's the equilibrium established. We know this. There are some other species in the system, but in the main, this is what you got. This is what you get when you saturate ionized water with silver chloride. Similarly, this is what you'll get when you saturate sodium nitrate with silver chloride. Because sodium ion, a main component of this system after I put the silver chloride in here, because hey, the molarities of sodium ion and nitrate ion are 0.10 molar. In the ionized water, the molarities of these are only 1.3 times 10 to minus 5. So what I'm curious about is, on dissolving the silver chloride in the sodium nitrate solution, will the molarities of silver ion and chloride ion still be that value? Because And I might well expect that, yes, they would, because sodium ion in solution. Does sodium ion react with either of these ions in solution? Based on your knowledge? Yes or no? No. Does nitrate ion react with either of these ions in solution? Based on your knowledge? No. So I'm saying, okay, so what? Now I got silver ion and chloride ion swimming around in the presence of a high concentration of sodium ions as well as a high concentration of nitrate ions, but these ions don't react with those. So I say, well, the molarity ought to be the same. Ha! But I find out that's not true. In this solution, SAgCl is considerably greater than 1.3 times 10 to the minus 5. Exclamation point. Chemist goes back to the drawing board, scratches his head. What the hell is going on here? Because what has gone on here is I've had a significant impact on the activities of silver ion and chloride ion. Because in straight water, if I've saturated straight water with silver chloride and get a silver ion as well as a chloride ion molarity of 1.3 times 10 to the minus 5, and I add a source of silver ion, wham, silver chloride precipitates. If I add a source of chloride ion, wham, silver chloride precipitates. But here, by adding these ions, neither of which react with the component ions of silver chloride, I've made the solubility of silver chloride get greater, considerably so. I don't remember what the values are, but I think it winds up being about 10 times more soluble, something like that. So maybe let's just put it this way. What's going on here? Well, tell me. Silver ion, not at a high molarity. Now swimming around, rather than in an environment strictly of water molecules, and other few silver ions and other few chloride ions, this thing is going to be swimming around in an environment that's rich in sodium ions and nitrate ions. Will either of these ions be attracted to this thing? Not chemically, but electrically. Why so, Coulomb? Is silver ion plus? Yeah. So is there a natural attraction between silver ion and nitrate ions? You're damn right. Coulomb's law tells us that. How about chloride ion? Will there be a natural attraction between chloride ions and sodium ions? Huh? You're damn right. Now then, when the nitrate ions swim towards silver ion, or silver ion swims toward nitrate ion because of Coulombic attraction, these nitrate ions aren't going to go by themselves. They're going to drag sodium ions with them, right? Because the most concentrated, by far, positive ion in this pot is sodium ion. So if nitrate ions are going to migrate, the sodium ions are going to migrate with them. Just like when the sodium ions migrate to this, the nitrate ions migrate with them. So what happens? Around this ion, I wind up getting a sheath of nitrate ions and sodium ions. And around this ion, I get a sheath, like a cloud, of sodium ions and nitrate ions. What impact does this cloud of these non-reactive ions wrapped around silver ion, as well as wrapped around chloride ion, what impact does that have on the ability of silver ion and chloride ion to get together and make silver chloride? Does that enhance that ability, or does that reduce that ability? Reduces it. It's like an insulating sheath. Consequence, up goes the solubility. Because what I have really achieved in doing is to increase the activities of silver ion and chloride ion. They now have the ability, in the presence of each other, to be present at higher concentrations without reaction, because they're prevented now more effectively from clobbering each other, because you're not going to make any silver chloride unless silver ion and chloride ion meet with each other. And now I have impeded the likelihood of silver ion and chloride ion from getting together. That's the salt effect. Why is it called salt effect? Because in order to make the solubility of a semi-soluble salt increase by something like this, I have to dissolve what kind of a material? A salt, an ionic compound, right? Salt's a general name for an ionic compound. The only requirement being is that the salt which I dissolve is two requirements. It's got to be fairly soluble in water, and it's got to be composed of ions, neither of which react with any of the component ions of the salt whose solubility I'm interested in. In this case, silver chloride. That's the salt effect. Enough said. Since I don't have any data which would allow us to make any direct calculation on this, well, that's not true. I have some. But I don't think it's worth our while to spend time to take a look at this, which really for us now is rather a sidelight. But it is part of semi-soluble salt equilibria, because the salt effect is ever so obviously a way by which solubilities of semi-soluble salts can be affected. So we go to D. Subcategory D of topics chronologically considered in Chapter 19. Something you have already been doing in laboratory, haven't you? Finding out about the presence or absence of an ion in solution by testing that solution with a reagent that contains an ion that has the ability to react with the ion you're looking for and make a precipitate. Calcium ion. Assignment 3, 46L. Tell me, what are the 4 salts of calcium ion? 4 salts of calcium ion that you have studied, or if you're still in assignment 3, are studying. 46L. Calcium. Calcium carbonate. That's 1. What else?
Calcium hydroxide.
Calcium hydroxide, that's 2. Calcium sulfate, and interesting stuff. There's the formula for the calcium sulfate that you investigate and in fact prepare in assignment 3. Calcium sulfate dihydrate. Common name for this stuff is gypsum. Did you ever make plaster molds when you were a kid? Or is everybody still so overtaken by this computer age that you didn't do anything when you were a kid except play with computers? I sure as hell hope not, but I don't know. One of the first wonderful presents my parents gave me, I think it was in the 5th grade or something. On TV, I saw a chess game in progress. I already told you about my passion for chess, didn't I? Well, that's the first time what's that? Look at this neat thing. All these things that look like men and horses and all that stuff. Not just checkers, just little things that... My father was a good checker player. I didn't care for checkers. But I looked at this chess and wow, that's neat. I want to learn about that. So that Christmas time, my parents bought me my first chess set. I think it cost $3. Little white and black plastic chess pieces. They were very flimsy and easily knocked over. Well, I had this, not gypsum, but plaster of Paris. To take plaster of Paris and turn it into gypsum, you just add water. You ever do that? Okay, well, so I took and added water to my plaster of Paris, and before it hardened, I poured it into my chess pieces, turned upside down, because they were hollow, and now I had pieces which had a lot more weight to them, so they wouldn't knock over so readily. Ha ha! Science at work. Okay? Interesting chemistry shown by this material. I believe I've already asked you this. How many of you had some practical experience with this stuff? Have you made any casts, for example?
I did in like art class.
Art class, okay, that's good. How about home construction? Huh? Do you know that calcium sulfate dihydrate is the main component of plasterboard? Also commonly called gypsum board or sheetrock. Any of you ever fix any walls at home? There's a wall, man. I've done this. You think that stuff is pretty soluble in water? You want to make walls at home out of sugar? You smudge the wall and mom comes along, whacks you on the hiney, and you mosey along going wah wah wah, and then she comes along with the sponge to clean off the spot. The wall dissolved. It's made out of sugar or salt. Hey, you don't do that. Use this stuff, not very soluble in water. Now, next question. You've seen plaster. You've seen wallboard. Does it cry? You see the water dripping out of this stuff? Because when water is mixed with plaster of Paris to make gypsum, voila, the chemistry turns water into the solid phase. How about that? Under normal lab conditions. Chemistry does marvelous stuff. Because water by itself is principally liquid, isn't it? And under normal laboratory conditions, it's never solid. It can be vapor, principally liquid, but never solid. Ha ha! That stuff, it's solid. All right, that's 3. What's the 4th salt of calcium ion that you studied in assignment 3?
Calcium chloride.
Calcium chloride. And you also know that you would never successfully test for calcium ions presence or absence in solution by trying to get it to precipitate as the chloride. Why not? Do you remember the calcium chloride solution used in lab is half molar? Does that sound like calcium chloride's pretty damn soluble? Yeah, you're not going to precipitate calcium ion as the chloride. But you can precipitate it as either of these 3 materials. And that's what detection of an ion in solution by precipitation in general is all about. I got a solution which may or may not contain calcium ion. But I do know it contains sodium ion because of my flame test. And the first thing you do in assignment 3 is to see if you can find out about calcium ion by flame analysis if sodium ion is present. What'd you find out? Sodium ion flame dominates. So you can't find calcium ion by flame analysis if the system contains sodium ion. So you've got to do a chemical test, precipitation test. And the precipitation test you learned about is getting calcium ion interact with hydroxide ion to make calcium hydroxide, or getting calcium ion interact with carbonate ion to make calcium carbonate, or getting calcium ion interact with sulfate ion to make calcium sulfate. That's the possible precipitation investigations that you performed and learned about. Okay? So, to find out about sensitivity, detectability of calcium ion in solution by precipitation, we'll take 10th molar sodium sulfate, 10th molar sodium hydroxide, 10th molar sodium carbonate. Because what this allows us to do is to compare the ability of sulfate ion at 10th molar versus hydroxide ion at 10th molar versus carbonate ion at 10th molar to go into solution and find calcium ion. Find it by reacting with calcium ion and see if you get a precipitate. Calcium sulfate, calcium hydroxide, calcium carbonate. Now, when we look at the KSP equilibrium for calcium sulfate, which is this equilibrium reaction. we get this equilibrium constant expression. And if sulfate ion is my precipitating agent, and sulfate ion is present at a molarity of 0.10, then tell me, at what calcium ion molarity, by using sulfate ion at 10th molar, at what calcium ion molarity can I expect to get calcium sulfate dihydrate precipitate? Calcium sulfate will have a chance to form in this system if the calcium ion molarity is bigger than what number? (9.1 times 10 to minus 5), right? All I did was to take this KSP value and divide it by this, and that's the molarity above which calcium ion must be present to have a chance to get calcium sulfate to form if my precipitating agent is 10th molar sulfate ion. Well, if I do the same thing with hydroxide ion, you can do the arithmetic. You find out that calcium sulfate is certainly much easier to form than calcium hydroxide. Put another way, what I've said is calcium hydroxide is a lot more soluble than calcium sulfate. But what about calcium carbonate? If carbonate ion is 10th molar, I don't even need to write the equilibrium. Here's KSP. So with this number, you can see that calcium ion molarity with carbonate equal to 10th molar, calcium carbonate has a chance to form if the calcium ion molarity exceeds what value? 6.2 times 10 to the minus 8. Done. And that's all this stuff is about. Now, one more comment on this. Notice that hydrolysis, in this case of carbonate ion, is not really much of an issue, because we're purposely going to fix the carbonate ion at 10th molar. Now, if you do some arithmetic on this, you'll find out that the carbonate ion molarity is a little bit smaller than 10th molar because of carbonate hydrolysis. But at this high concentration, the hydrolysis extent is not all that great. Even though at this high concentration, you're going to get a much higher hydroxide ion concentration than you will get at any lower carbonate ion molarity. You can do the arithmetic to find that out. Pick it up from this point next time.